Hi everyone, and welcome to Erik's Electronics Workbench. So on the bench today I have this Stanford Research Systems model DS340 15 MHz synthesized function generator. Now this particular instrument has developed a problem and it's displaying a fault code when it starts up. So follow along as I do the troubleshooting and repair and see what it takes to put the instrument back into service. So let's get started. So the Stanford Research Systems model DS340 looks like it's in clean condition overall. I don't see any physical damage to the outside of the instrument, so it looks like it was well taken care of over the years. But nonetheless, it does display a fault code when it's starting up, so we'll get into that in just a moment. Now, as a quick overview of the instrument, it uses a technique known as direct digital synthesis to create the various waveforms, and it's able to produce sine, square, ramp, triangle, noise, and arbitrary waveforms. So the sine and square waveforms are adjustable from 1 microhertz to 15.1 megahertz with a 1 microhertz resolution on the display. The ramp and triangle waveforms are adjustable from 1 microhertz to 100 kilohertz, and the arbitrary waveform uses a 40 megahertz sampling rate. So very usable frequency ranges and capabilities. The output amplitude is adjustable from 50 millivolts to 10 volts peak to peak into a 50 ohm load, and if you're driving into a high impedance load, the output is adjustable up to 20 volts peak to peak. The arbitrary waveform goes from 10 millivolts to 10 volts peak to peak in 50 ohms, and if it's a high impedance, of course, it can go up to 20 volts peak to peak. Now the instrument is always a 50 ohm output on this connector right here, and when you're driving a high impedance load, you can select that it is set for high impedance. It doesn't change the internal impedance, but it makes the displayed value for voltage match more closely with what's actually being supplied by the instrument. In other words, the output isn't being loaded down or pulled down as much by a 50 ohm load when it's connected to a high impedance load. So roughly the output voltage cuts in half if you go from a high impedance down to a 50 ohm load. So it just makes the display match the output more closely. But again, it's always a 50 ohm internal impedance that the instrument has. The instrument can also do frequency sweeps in linear or logarithmic modes, and it has the ability to do frequency shift keying. So some nice features that the instrument has. So let me power up the instrument and take a look and see exactly what the fault code is, and then I will connect the output to my oscilloscope and frequency counter. Let's see how it actually looks without doing anything else, and just see what the outputs are. How the calibration looks, is the amplitude matching the displayed value, is the frequency matching, and so on. Just kind of get a feel for exactly what the issue is. Again, this instrument was reported to have something wrong with the calibration, so we want to take a look. That means something must be inaccurate on the output versus what it displays. So I will go ahead and power it up, and then we'll start on that troubleshooting. So I'll reach around here with my power cord and get this connected. Okay, let's take a look and see what this actually does when it powers up. Okay, there's the error. So it said cal D error, so it does make sense there's a calibration related error. Okay. So what I will do is I'm going to set the instrument, it's on the frequency mode right now. Let's set it to, let's say 10. Let's try megahertz there. So it is accepting inputs by the keypad. So we've got 10 megahertz, and we'll see if that 10 megahertz matches what shows up on the frequency counter. We'll take a look at that in just a moment. Let's set the output amplitude. It's already on 1 volt peak to peak, and that's what I was going to select. Let's see what happens if you go, like, let's say 2 volts. So there's 2 volts peak to peak, so it does accept inputs there, no problem with that. I can hear some relays clicking, so it sounds like the attenuator sections are probably working okay, some activity internally, so that's always good to hear. But let's see here, if we go shift, and then here's the high impedance, so yep, you can see that it does select that, and you can see the high impedance when it's selected it, the voltage value doubled. It went from 1 to 2 volts peak to peak. Shift, at 50 ohms. I will keep it on 50 ohms because I'm going to terminate the output into a 50 ohm pass-through termination on the oscilloscope, and also the frequency counter has a 50 ohm input. So I'll leave it on that. So we've got 1 volt peak to peak, and we'll go back. The frequency still on 10 megahertz. All right, so let me get this connected to the oscilloscope and also the frequency counter, and I'll reposition the camera. I'll be back in just a minute. All right, I now have the DS340 function generator connected to my Tektronix TDS724D oscilloscope. Now you have to pardon that sort of rolling effect that you see on the oscilloscope's display. It's not something that I can see when I look directly at the oscilloscope. However, it's basically the refresh rate of the oscilloscope's display not playing nice with the camera. So aside from that, we can see that the displayed waveform actually looks pretty reasonable. I don't see any serious issues. The displayed frequency looks very close to 10 megahertz. It looks like it's shifting around just a little bit there, but it is pretty close to 10 megahertz. The displayed peak-to-peak value is also very close to 1 volt. It looks like about 984, 992, so very, very close to that 1 volt peak-to-peak value. Now, I mentioned that the function generator has a 50 ohm output, and you can see I have a pass-through termination right here on the end of that coax cable. So this is a 50 ohm pass-through termination, all right? So it keeps that peak-to-peak voltage value correct because the function generator sees a 50 ohm load. You can see if I take that termination off and just connect it directly, you can see how large that amplitude rises to, all right? Because the oscilloscope is a very high impedance input, so it doesn't load down the function generator as far. All right, so again, back with the 50 ohm impedance there with the 50 ohm pass-through termination, and the waveform again looking very good, but let's take a look at the frequency on the frequency counter and see how close that is to 10 megahertz. So move this over and connect it up here. Now the frequency counter has a 50 ohm input. I need to select that right there. Okay, so we don't need that pass-through termination because again the termination inside the frequency counter is now set for 50 ohms. So the frequency, it looks like it is under 10 megahertz, but not by too much, but that really should be right on at 10 megahertz. So that does match up with that idea that there is a calibration problem, that CalD error that came up. But it's, again, not too far off, so good to see, but it does need some adjustment. So the next thing that I will do is to open the top of the instrument, and let's take a look inside. And let's see exactly what's going on with this calibration problem and that CalD error. I'll reposition the camera and I'll be right back. I now have the top cover removed from the Stanford Research Systems DS340. The cover removes very easily by just removing a screw that's on the 4 corners right here. Top cover lifts right off. Looking inside the instrument, it looks very clean. There's almost no lint or dust, anything like that inside the instrument, so it looks like it was well taken care of, and even the cooling fan right here has really no lint on the fan blades. Now, if you're following along and working on an instrument like this, please know that you do so at your own risk. There's exposed AC line voltages in the back of the instrument. AC line, of course, comes in on the back panel, and there's certainly some high voltage back here. This is the power supply section. So know the safety measures and precautions necessary if you're working on an instrument like this. And again, if you were following along, you do so at your own risk. So the way that Stanford Research Systems has set up the calibration in this instrument is that there are a few select physical adjustments that are done on the main circuit board, but the majority of the adjustments for calibration are done in software by calibration factors. Stanford Research Systems uses the term CalBytes, C-A-L-B-Y-T-E-S, okay, so CalBytes. And there are literally hundreds of these CalBytes, or correction factors, that are permanently stored in ROM, which is read-only memory. So there's a ROM chip that's on the main circuit board. When the instrument is created or built at the factory, the calibration is set up and it's permanently coded into that ROM chip, all right, which is very handy because that ROM chip is always there. It doesn't require a battery or anything like that, and the data is always there. And that data is good as the instrument leaves the factory. Now, over time, things can age, and one of the things that can certainly age is the crystal oscillator, okay? So Stanford Research Systems, particularly in their service manual, they mention that the one cal byte that you will probably need to adjust over the time is the calibration factor for the crystal oscillator. And we did see that the frequency was off by a little bit, okay? So it makes sense that that cal byte may need to be adjusted. Now here's the thing and how it operates. The ROM cannot be changed, all right? However, when the instrument is powered up, all of the data for these cal bytes that is held in ROM is moved over to RAM, or random access memory, and that RAM is battery backed. And we do in fact see a battery right here. Okay, this is of course the back side of the circuit board. The other side is where the battery is down here, and it's soldered there and over here. Now, if this battery has become weak or is dead, the RAM won't hold up when the instrument is turned off. Now, here's why the RAM comes into play. The calibration factors, or cal bytes, may need to be changed. So what happens is, when the instrument is powered up, if the RAM is corrupted or is empty, it will move a copy of the data from ROM over to RAM. It should be held in RAM, and then you can change the data that's in the RAM as needed if the instrument needs to be calibrated. So again, we're seeing that the frequency is off by a little bit, and that could be corrected. The cal byte that is related to the frequency is something that could be adjusted. And it can be done so on the front panel. And over here, there is a jumper on the circuit board that is moved over actually where it is right now, and that gives access to changing the cal bytes if it's stored in the other position. That's the position that locks out the ability to change the cal bytes. It was already in the position for allowing changes, so someone else may have already been in there trying to change those cal bytes. Now again, the factory set of cal bytes stored in ROM should be good for most of the adjustments, because the rest of the circuitry in here really doesn't drift over time. I mean, it's very, very stable. But the crystal oscillator certainly can drift over time and needs some correction. So as it is now, if we go in and make a change on the data that's in RAM, if this battery is dead, it will be lost, and the next time you power up the instrument, you'd have to start all over again with a new calibration and taking care of that. That Cal D error that we saw in the front panel is a big clue that this battery may in fact be dead or very, very weak. Now, Stanford Research Systems, they mentioned that if the Cal D error comes up infrequently, it's really not a cause for concern, and if the instrument is otherwise performing okay, it's really not a problem. But if it's coming up often, which it does on this instrument every time you turn it on, that is a cause for concern, and it often means a problem with the battery. More serious, it may mean that there's a problem with the RAM chip or something like that, but the battery is the most likely thing. So let me grab my voltmeter and let's test this battery and see if it is in fact good or if it is bad. I'm going to move that over just a little bit, get the voltmeter in the shot here. So if I reach in here, and look at that. So looks like that battery should be, I believe it's a 3-volt battery, or a 3-volt lithium. Yep, that's definitely depleted, really nothing there. So knowing that that battery looks depleted, the next thing that I will do is replace that battery. So I'll get that taken care of. And then we'll power up the instrument, and let's take a look at those cal bytes and see what it takes to bring the frequency back into specification again. So I'll get started on that, and I'll be back when the battery is replaced. All right, the old battery is removed, and you can see it's a lithium 3-volt. The type is a BR 2/3 A, and just has solder tabs on it. Solders right onto the circuit board. And the new battery, direct replacements, exactly the same type. So I'll get that installed and we'll continue on. Okay, the memory hold-up battery has now been installed. So let's power up the DS340 and see if that calibration error is cleared. So let's see what happens. Now that's actually to be expected because the battery having been, depleted, the RAM had no information stored in it. So the instrument at this point has moved the data from ROM over to the RAM chip. A copy of the cal bytes have been moved over. So let's power down the instrument. Okay. Now the memory retention battery should be holding up the RAM. That data should remain. Okay, so we'll just give it a little bit here. And it should now start up correctly because all of the calibration constants are being retained in RAM. Okay, a copy has been moved over. And then we'll proceed, if that is true and there's no further issue, we'll proceed with changing the cal byte that's related to the frequency, because that seems to be where most of the calibration error is occurring as far as the deviation from where it should be. And we already saw that on the frequency counter. It looks like the amplitude was doing okay. We'll take a closer look at that as well, but I don't think it's too far off. Okay, there we go, test pass. So that looks very good. So it looks like that memory hold-up battery was the issue and was what was causing that calibration error. So at this point, I'm going to let the instrument run for at least a half an hour, maybe even 45 minutes or so. And I will also put the top cover on it. It needs to come up to just a normal operating temperature before any adjustments are made to the calibration for any of the settings. You don't want to do any calibration on the instrument while it's cold, because as it warms up, particularly the crystal oscillator will change just a little bit in frequency. So it needs to stabilize. So I will let it run here, and then when some time has gone by, I will continue on. Okay, the DS340 has now been operating for over a half an hour, so its internal temperature has stabilized, and I can now continue with the adjustment on the main oscillator, and that will be done by changing the cal byte value that controls the main oscillator's frequency. So I'll show you how to do that. Now you can see the front panel is indicating 10 megahertz. That's the value that I've entered right now for the main output frequency. However, on the frequency counter, it's actually indicating 9.9998960 megahertz. So a little bit low. We need to bring that up to very, very close to 10 megahertz. So while I'm making the adjustment, I'll keep the camera focused on the frequency counter instead of the instrument, so that you can see the effect of the adjustment that I'm making. You can see really what the actual output frequency is. If I go between the two frequency counter and the DS340, it's just a lot of extra camera movement. So let me show you exactly how you move around in the settings for the cal bytes. And it is really quite simple. First of all, you need to have the jumper on the main circuit board set to the position I previously talked about, which gives access to the cal bytes. And then you just press Shift and the number 9 key, and that brings you into the cal byte settings. So on the left-hand side of the decimal point, this is the cal byte, and cal byte 0 is actually the one that we'll be making the adjustment to. That's for the main oscillator frequency. And on the right-hand side, that's the cal byte value. 2174 is the factory preset, basically. It's the value that the instrument left the factory with. If you mess up the cal bytes and really need to start over, there is a procedure to reset the cal bytes, clear out the RAM, and it will reload all of the cal bytes from ROM again, and you can start all over. So really, you can get back to a starting point if you really mess up, particularly if you make adjustments to the wrong cal byte or lose track of where you're at or something like that. So it is a way that you can restore the instrument, basically. So with the cal bytes over here, with this value flashing, if you need to change this, and there are a total of 642 total cal bytes, so quite a few in the whole system, affecting many different aspects of the instrument, attenuator settings, output amplitude, and so on. If you need to change this value, let's say you want to go to cal byte 16, you could hit 16 like so, press that. So that would be displaying cal byte 16. You can see the value over here is the actual cal byte value, so 65,535. And that's actually what that should always be set to. That's the pre-attenuator's reference value. So if we want to go back to cal byte 0, just press 0 and like so. Takes us back there. Now to put the flashing digit over here so that we can make a change to this value, just press Shift like so. This is now flashing. You can change this by typing in on the keypad if you want to change the number, entirely. So you could actually type in, say, 2175, make a complete change. Press like that. That locks that value in. If you want to go back and step down one, go like so. That changes it like that. Step back up. So very easy to navigate around. And when you're completely done with making these adjustments, you can just press frequency. That takes you out of the calibration setting, and the numbers that you've entered are remembered and are now stored in the RAM chip. So when the instrument starts up, the values in RAM are preserved by that memory backup battery, and it will continue on with all of the calibration settings intact. So really is just that simple. Again, Shift and 9 will put us back where we need to make the adjustment. So let me put the camera up on the frequency counter and I'll start making this adjustment, and I'll just step this up because I don't know how much of an adjustment, I'm not going to type in a completely new number. What I will start doing is just incrementing this one step at a time, and I'll read off the number that I'm seeing here, and you'll be able to see the effect up on the frequency counter. So I'll reposition the camera. Okay, here we are looking at the frequency counter. So I'll start by changing that cal byte value, 2174. Let's step that up, so 2175. See if we're going in the right direction here. Yes, it is. It's increasing that frequency. So I'm at 2178, 2179, 2180. So it looks like we have a little ways to go here. I'm going to step it up a number of settings here. 2206 now. It's 2230. $22.56. Getting closer. That's 2290 for the cal byte value. $2310. $2320. Getting much closer now. It's 2325. There's 2330. And right there is 2331. Cal byte value 2331. So that actually looks really good. Now this Hewlett-Packard 5334B frequency counter is very accurate. I already calibrated this instrument, and you can see that calibration and how I did that in another video. So that's looking really spot on, right at 10 megahertz right there. What I'm going to do is let the instrument run now for a number of minutes, say 10 or 15 minutes, and let's see if it continues to hold at 10 megahertz. Okay, so I'll continue on in a little bit. Okay, here we are about 10 minutes later, and you can see how the frequency has stabilized to the way it's showing on the frequency counter. All nines or toggles over to 10, not a problem with that. So it's right at 10 megahertz, so looking very good. I took the cal byte and increased it by 1 digit more, okay, and that basically made it several hertz above 10 megahertz. So the cal byte setting of 2331 ended up being as close as possible to that 10 megahertz value. It really can't be made any more accurate or any closer than the way it is now. So looking very good. If I go to, let's say, 1 megahertz, try that. So 1 megahertz on the DS340, and that looks very good as well. So all nines on the display like that, not a problem. That's right at 1 megahertz. So now I will reconnect the output of the instrument over to my Hewlett-Packard 3456A voltmeter, And let's take a look and make sure that the output amplitude is accurate and correct. So I'll do that now, and I'll reposition the camera. Okay, I now have the DS340 synthesized function generator connected to my Hewlett-Packard 3456A digital voltmeter. So you can see over here the coax cable coming up to the adapter for the front panel banana jacks. So turning our attention back over to the digital display, you can see it's indicating 50 millivolts. So on the DS340 I have it set to a 1 kilohertz sine wave, and it's also set to 50 millivolts RMS. So that's looking very good. So let's try 100 millivolts RMS. All right, so there's 0.10 on the DS340's display, and we can see 0.100. Again, disregard the digits after that because the accuracy, on the DS340 doesn't go over that far. So looking very good at this point. No problems with those values. I'll just increment it now by 100 millivolt steps. So there's 200 millivolts, 300 millivolts, 400, 500 millivolts, half a volt right there. That's looking very good. So again, that's 0.50 on the DS340 display. So that's being reflected over there on the digital voltmeter. Very good. 600 millivolts, 700 millivolts, 800 millivolts, 900. Yep. And now on the DS340 it says 1.00. All right, for 1 volt, and that accuracy looks spot on. No problems with that. So if I enter, let's try 1.01. Yep, that looks very good. So 1.01 on the DS340 display, and we see 1.01 on the digital voltmeter over there. That looks very good. So let's try, let's say 4 volts RMS. Yep, no problem with that. And let's go, let's say about the maximum, there's about 7 volts RMS. It might go just a touch over that, but it's pretty close to the maximum. And no problems there. So it says 7.00, and we can see 7.0 and then 4, so about 40 millivolts higher. No problems with that. That's very close. So at this point, the DS340 is looking, very good. Its performance is looking really spot on. No issues whatsoever. Okay, I now have the DS340 synthesized function generator connected to my Hewlett-Packard 3585A spectrum analyzer. The DS340 is set to 1 megahertz sine wave output. So the spectrum analyzer is sweeping from 1 megahertz to 10 megahertz. So that will allow us to see up to 10 harmonics if they're present. And as you can see on the spectrum analyzer's display, it does show a couple harmonics showing up. Several of them are there, and then by the time it gets closer to the the 10th harmonic, they're basically buried down into the noise. They're very, very low values. Pardon the flickering on the spectrum analyzer's display. It's basically the refresh rate, not cooperating with the camera, similar to what we saw on the oscilloscope earlier. So the marker right now, I'll move it over. And you can see right there that is on 1 megahertz. And you can see that the actual value is 12.1 dBm. The reference line, or the top graticule line on the spectrum analyzer, is 15 dBm. So keeping in mind that this is a logarithmic scale, these harmonics that are showing up, the 2nd, 3rd, 4th, and 5th harmonic right there, are actually very low values. So I move the marker over to that 2nd harmonic, about there. You can see it's basically at 2 megahertz. And you can see that's also down about negative 47 dBm. Go to the 3rd harmonic. Up there, 3 megahertz. And we can see that's about negative 37 dBm, roughly. Go to the 4th harmonic. There, about 4 megahertz. About negative 54 dBm. I'm pretty quite low there. And see, that's about the 5th harmonic right around there. It's about negative 54 dBm, roughly about there. Find the 6th harmonic would be at 6 megahertz, of course. know if we can see that very well. It's pretty low. It would be right about there where the marker is. Pretty much down in the noise, very, very low value. Now if I switch the function generator over to the square waves output, so now it's at 1 megahertz with a square wave, we can see the harmonics rise up substantially, and that's to be expected. That happens with a square wave. So you can see all the harmonics show up, very easy to see. All right. So you could go over here all the way over. If you go to the 10th harmonic right there, 10 megahertz, no problem seeing that. And in fact, if we do a complete sweep from, well, this is extending out basically to 40 megahertz out here now. The span, you can see, it's quite wide, and the center is 20 megahertz, of course. You can see the harmonics for the square wave. There's many of them there, and they extend all the way out. But again, to be expected with a square wave output, that happens. You go back to the sine wave, of course, those harmonics disappear. So looking very good at this point. You can see the original harmonics we were looking at now are all scrunched over to the left-hand side of the display because the span is so wide at this point. So if I go to start frequency 1 megahertz, stop frequency 10 megahertz, puts us back how we were originally. So looking very good at this point. The output is very stable, but the frequency is very accurate. The amplitude is really spot on, no problems with those values and readings and how the instrument is performing at this point. So the DS340 is ready to put back in service and is functioning correctly. So if you enjoyed this video, don't forget to give it a thumbs up. And if you're enjoying the videos on this channel, please remember to subscribe. There'll be many more videos like this coming in the near future. So thank you for watching, and until next time, take care. Goodbye for now.